Dear students, welcome to the online class. I am Dr. S.C. Hremat. In the previous videos of Debye Huckel's theory, we derived the kappa equal to 4 pi e square summation of ni zi square divided by d k t raised to half, that is square root of this. Okay, we have derived one equation in the first video, and we have also derived the expression for energy. The energy of a charged body that is given by ER equal to or ER or EI, ith ion, that is equal to Zi square, then E square, then kappa divided by D. This is with negative sign, and 1 divided by 2 may be taken as equal to 2. Okay, this is equation 2. Now let us take this equation as 1, and this is equation 2. For 1 mole of ions, that is an Avogadro's number of ions, energy, that is E equal to N, that minus as it is, just multiply it with N Zi square E square, then kappa divided by 2D. Okay, now this is equation 3. Okay, in the previous classes we have derived the expression for this kappa, and also we have derived the expression for an ion, means we converted into for 1 mole of ions. From thermodynamics, we know chemical potential, of a particular ion in an ideal solution is given by mu equal to mu naught plus RT ln x, or where x is the mole fraction of the ion. For non-ideal solution, this equation, suppose this is equation 4, becomes mu equal to mu naught plus RT ln x into activity coefficient F, and this may be written as mu naught plus RT ln x plus RT ln F RT ln F. This is activity coefficient of an ion. For particular ion, we may take it as Xi, Fi. Suppose this is equation 5. By subtracting equation 4 from equation 5, we get this equation may be written as mu I dash. This is mu I and mu I dash. This is for the ideal solution and this is for the real solution. By subtracting equation 4 from equation 5, you will get mu I dash minus mu I is equal to RT ln F I, where Fi is the activity coefficient of ith ion. The change in chemical potential may be potential that is mu I dash minus mu may be taken as equal to free energy change which is equal to energy of a charged body from equation 3, that is RT ln Fi is equal to, let us take it as the energy of the body, minus Zi square, that is N into Zi square E square kappa divided by D, that to 2D. Suppose this is equation 5. By substituting kappa from equation 1 in equation 5, we get ln Fi is equal to minus N Zi square E square divided by 2D. Then you substitute the value of K, that is 4 pi epsilon square summation of Ni Zi square divided by dkt, this raised to half. It can be rearranged. This equation can be rearranged as minus N E square divided by 2D. Then we want to take D at last. then we may write 4 pi e square divided by d k t raised to half. Then you take zi outside, zi square, then summation of ni zi square raised to half, raised to half. For unit volume of solution, for unit volume of solution, suppose 1000 ml, Ni, that is number of moles, may be taken as equal to concentration, in moles per dm cube, then summation of ni zi square may be written as equal to summation of ci zi square, by dividing by 2, we get 1 by 2 summation of ni zi square equal to 1 by 2 summation of ci zi square, which may be taken as equal to, here 1 by 2 summation of ci zi square may be taken as equal to mu, that is ionic strength, that is equal to ionic strength. By substituting this, in equation, suppose this is equation, that is 5, 6, and this is equation 7. We get ln fi equal to minus ni e square divided by 2d, then 4 pi e square divided by d k t raised to half, then zi square, then 2 divided by 2 summation of ni, that is ci zi square, this raised to half. This may be taken as equal to minus n e square divided by 2d, then here we may take root 2 this side, and this becomes 4 pi e square divided by d k t raised to half, and this is taken as equal to mu, that is equal to z, let z be as it is, zi square, then root mu. Now this equation here, all up to this point, all these are constants. It may be taken as equal to a, then this is equal to z I square, then root mu, where 2, then 4 pi e square divided by dkt raised to half is equal to a. Suppose this is equation 7 and this is equation 8. Equation 8 is known as equation that is f ln f I equal to this. Equation 8 is known as Debye Huckel's limiting law. Then limitations. Limitation of Debye Huckel limiting law. This law is applicable only to the dilute solutions of strong electrolytes. Debye Huckel's limiting law in terms of mean ionic activity coefficient, that is F plus or minus. For strong electrolytes, having valencies of positive ion or negative ion more than unity, then equation 8 is modified as ln f plus or minus equal to minus a z plus z minus into root mu. Suppose this is equation 9, where f plus or minus is mean ionic activity, coefficient, and z plus is equal to valency of positive ion z minus is equal to valency of negative ion. In the above Debye Huckel limiting law, that is ln f plus or minus is equal to minus a z plus z minus square root of mu. In this equation, a is constant. Z plus and Z minus are also constants for a solution of a given salt. Then ln f plus or minus varies linearly with root mu. By plotting a graph of ln f plus or minus, let us take it as a minus, versus root mu, we expect a straight line passing through origin and slope gives the product of valencies of ions. That is we can plot a graph of, it is root mu, and here this is minus ln f plus or minus. Okay, we may take minus here or we may take minus here. One term is minus and another is plus. Now we get one line like this, that is slope equal to 1, that is z plus into z minus is equal to 1, that is for univalent ions. This is for univalent ions. Now you take another curve. Here slope equal to 2, then z plus into z minus is equal to 2, then bivalent univalent ions. Similarly, this is equal to slope equal to 3, then z plus into Z minus is equal to 3. Then it may be trivalent and univalent. Univalent, trivalent salt. Univalent, trivalent, valent ions. Ions. Here, if we get a straight line passing through the origin, it shows that the salt is obeying the Debye Huckel's theory of strong electrolytes, that is Debye Huckel's limiting law. You know, Debye Huckel's theory of strong electrolytes is applicable only to the dilute solutions. That is, Debye Huckel theory is applicable to the dilute solutions of strong electrolytes. That is, Debye Huckel limiting law is applicable to dilute solutions, and it is not applicable to concentrated solutions. Bronsted applied corrections to Debye Huckel limiting law, allowing for polarization of solvent molecules around the ion in a solution of higher concentration. The modified Debye Huckel limiting law is, that is, ln f plus or minus a z plus z minus square root of mu plus c mu, where mu is the ionic strength of solution, and C is a constant. This equation is known as Debye Huckel Bronsted equation. It is applicable to the solutions of all concentrations that is higher concentrations. At lower concentrations, F plus or minus is nearer to unity, whereas at higher concentrations it is much smaller than unity.